Hello people, I just want to do a quick chat about polymers. I made a polymers video, Ofsted was in, I got a bit twitchy, so I thought I'd just do it again, just you and me. You did addition polymers last year. The idea of an addition polymer is that the carbon-carbon double bond breaks and makes a single bond and two new bonds extending to the rest of the polymer chain. So the simplest possible polymer to make is polyethene or polythene. So if we have an ethene monomer, the name of the polymer is just poly, written in front of the monomer name, which obviously everybody just calls polythene. Polythene is a very versatile and fairly strong plastic, which is used in carrier bags and supermarket milk bottles and all sorts of other plastic stuff that we handle on a daily basis. Just a difference between the structure on the screen, which was when you were asked for the GCSE formula of the polymer, you always put it in curvy brackets with an N after it. So that's the formula for the polymer. At A level, we more often use the repeating unit of the polymer, where we don't worry about the brackets and the N. We simply draw the fragment as it is with leading and departing bonds going either side out of the molecule, showing what it's attached to. So ethene, as it says on the screen there, it's made into polythene, high temperature, high pressure, and in the presence of a catalyst. It's a free radical mechanism, but you don't need to know about the mechanism. And the common examples for polymers are chloroethene, propene, tetrafluoroethene, and phenylethene or styrene. I'll just give you a moment to have a go at writing the structures. You just pause the video. And I'll put the structures on the screen now. So they're actually all formulas with the brackets and the N, but it's the same if there's the repeating unit. It's the same chemical structure. So the various uses of, well, polychloroethene. Chloroethene used to be called vinyl chloride, so polychloroethene is the same as PVC, which is the tough, rigid plastic used to make drain pipes and guttering. UPVC windows, the U stands for unplasticized. Remember, plasticizer is the molecules that are put into the material to keep the polymer chains apart, and that makes the polymer less rigid, more rubbery, more flexible. Obviously, you don't want window frames to be rubbery and flexible. The glass would just fall out. So that's UPVC or PVC. Propene, so polypropene is used to make things like plastic tubs for margarine or yogurt. Polytetrafluoroethene, PTFE, is used to make, its brand name is Teflon, which is the black material inside saucepans that stops your fried eggs from sticking to the saucepan. It's also used in wax jackets, so, sorry, not wax jackets, they're covered in wax. Gore-Tex jackets, that's what I meant to say. Gore-Tex jackets, which have a PTFE lining that repels the water. And, some pickies. Of course, vinyl. PVC is vinyl, which is used to make records. Polystyrene, when it's expanded with carbon dioxide, it makes those lovely, satisfying, foamy, soft plastics that is used for packaging. The rigid lumps of polystyrene is used to house your shiny new telly. And I mentioned polyethylene is used to make supermarket milk bottles. There's two forms of polyethylene. High density polyethylene, where the chains are generally straight, makes again a hard rigid plastic suitable for holding litres of milk. Low density polyethylene is made in a slightly different process, and the chains tend to be branched, and that means they can't get as close together, so the intermolecular forces are weaker, and that means that the plastic as a whole is weaker and has a lower melting point. So that tends to be used for cheap supermarket plastic bags, that kind of thing. Very, very cheap material, fails very easily. The problem with plastics is, of course, plastic pollution. Plastics end up in the environment. They are very robust materials. They tend not to break down, which is a good thing if you want to keep something in a plastic container for years, but it's less good if the plastic ends up in the ocean or in the environment, destroys habitats and just looks very unpleasant. The reason for that is your carbon-carbon chain, which is the root of the polymer, doesn't contain any polar groups. So the plastic as a whole is non-biodegradable. There's nowhere where the enzymes or the bacteria can kind of get in and chomp their way through the plastic and break it down. The plastics do physically break down. They get battered by wind and oceans and so on, and they get broken into smaller and smaller pieces, but they never finally kind of dissolve away, and you end up with microplastics, which are just very, very tiny bits of plastic, which are now found all over the planet, including in you and me, in our food, in the air, just everywhere. Okay, so that was a quick whistle-stop tour through addition polymers. Condensation polymers are made by condensation reactions, and we talked about various types of condensation reaction. The two that you should know about are where we react an alcohol with a carboxylic acid or a carboxylic acid derivative, and then an amine with a carboxylic acid derivative. So got a couple of reactions there. So methanol and ethanoic acid makes what? Ethylamine and ethanoyl chloride makes what? Just pause the video and write the structures for those. So just use a bit of colour here. The ethanoic acid and the methanol react by losing, there's always a small molecule that's lost. In this case, it's water. And we talk about the structures being condensed slightly as they move together. So we end up with the, that was actually a blue O, wasn't it? Now I've made a mess. There we go. So the structures become condensed slightly, and that makes the ester methyl. Remember, we name esters from the alcohol end first. Methyl ethanoate. And it's a similar reaction, but with the acid chloride. I've got a chlorine there, and then just do the amine like that. So this time with the acid chloride we'll lose HCl. Of course there is a mechanism for that reaction which you should know, the addition elimination mechanism, but I'm not going to go over that now. And that makes this new functional group here, just point that out. That functional group is the amide. And then, so the name of that would be, well, I've got an ethyl group on the nitrogen, so that's N-ethyl. And then I've got 2 carbons on the amide end, so ethan. And then the name ending for amides is just amide. N-ethyl, ethan, amide. If I have a molecule with 2 functional groups in it, so here's my molecule. I've got an OH at one end, and then I've got a carboxylic acid on the other. Then the molecule can react with itself. I mean, I suppose it could conceivably kind of bend around and form a tight little ring there, but it's more likely to bump into another of itself. So this acid group could react with the alcohol group in another molecule. So we can imagine that that acid there would form an ester with another molecule there, and then we'd have the rest of this molecule here, but then it would go on, and we'd have another acid there reacting, and we'd have another alcohol here reacting, and the polymer chain would just extend and extend and extend. So I've actually drawn 2 repeating units for that polymer there. So let's just rub out one of them so it's a little bit clearer, like that. So, sorry, that's wrong. I've got too many oxygens. Okay. So this oxygen would then bond to another of the molecule. So that will be our repeating unit for this polymer. Now you can get polymers made in this way. The trouble is, if a molecule can react with itself, then if I put it in a container and leave it in the cupboard for 6 months, when I go there I might find I've just got a bottle full of polymer. If it can react with itself, then that's going to happen. So it makes more sense to have 2 different monomers and to mix them together only when I want to make the polymer. So here I've got a monomer and a polymer. Just pause the video, see if you can name these 2 molecules. So this would be 2 carbons is eth, but we've got 2 ols, remember, di has an E in it, so it's ethane 1,2 diol. This is called benzene dicarboxylic acid. Oh, it should have a 1,4 in there somewhere, shouldn't it? Benzene 1,4 dicarboxylic acid. The reaction that takes place is the same reaction to make an ester. So if I take the OH and H away to make my water, and then I stick them together. So that CH2 there is going to go straight into the ester. Then we'll have the benzene ring. Then we'll have the rest of the carboxylic acid there, and then I've got the other end of the molecule. But when I get to this O, then that's going to connect to the rest of this ester here. So I've got an ester group there, but I've also got an ester over there. So yes, it's a polyester. The name of this polyester, well, if I told you that this used to be called terephthalic acid, and this used to be called, just trying to work out my pens, ethylene diol, then you might be able to work out that used to be called terylene, sometimes called dacron as well. So dacron, unlike the addition polymers, which are mostly made into plastics, hard plastics, containers, polyesters are used to make the kind of clothes that most of us are wearing today. So polyesters and the polyamides we'll come to in a moment are fabrics, and they can be woven and spun and manipulated. They're often mixed with natural fibres like cotton and silk to make a variety of types of garment and cloth. Because they do have polar groups in, polyesters and polyamides are biodegradable. I mean, not hugely biodegradable. They won't break down like a banana skin breaks down in your compost in a few weeks, but they will break down eventually. It might take years, but they will break down. So you sometimes see in the supermarket, you'll get a bag of like organic carrots, and it's in a biodegradable plastic bag. So they've just used polyester or polyamide to make that biodegradable plastic. I'm looking around the room because often lads leave behind plastic bottles, but they've all been squirreled away. But your standard plastic water bottle that you get from supermarkets and shops is made from PET, and that is polyethylene terephthalate is similar to this. It's prepared in a slightly different way, and that makes it into a hard plastic, but again a bit more biodegradable than polythene. The last thing I want to look at is the polyamides. So polyamides are made from amines. Oh, I was going to get you to name these, but the names are on the screen. So if I take an acid chloride and an amine. Remember, we looked at this earlier, didn't we? Then HCl is removed as a small molecule, and I make that new amide linkage between the two. And then, of course, the rest of the molecule is just going to be there. So we've got 6 CH2s on the amine side and 4 CH2s on the acid chloride side, but then that acid chloride is going to combine with a new amine to make another amide, so that bond goes into there. So that's the repeating unit of our polyamide. So polyamides are often referred to as nylons. Nylons again are tough fibers that are used for clothing, usually for tougher clothing like outdoor coats, tough outdoor coats or tents or sailcloth. They can be made into very, very tough fabrics that will resist weather and the elements and so on. A special polyamide or a special nylon is Kevlar. So Kevlar is made from this stuff, terephthalic acid, 1,4-dicarboxylic acid, and a similar looking amine where we've got a benzene ring in the middle, 1,4-diaminobenzene. If I react those together, so again, I'll get my new amide functional group joining the two benzene rings. That's the worst benzene ring I've drawn for a while. And that, again, that bond would connect to another nitrogen there. So that's the repeating unit of the polymer. But in this case, because of the regularity of the benzene rings, still rubbish, the regularity of the benzene rings, the molecule chains will form strong intermolecular forces with each other. They stack in a very predictable way, and that makes the plastic especially, or the material especially rigid, which is why it's used for bulletproof vests. So Kevlar is a combination of good chemistry to make the chains, and then good engineering to make a material which is literally bulletproof. Thanks, folks. Take care now.